Here we are at example 5b from our 5.1 set of notes. We're asked to use the properties of exponents to solve for x here. And on the left side, we notice that there are some things going on. The right side is kind of nice and clean, it's just the number 25. But on the left, we can actually kind of use some properties with exponents, more specifically our quotient property with exponents. So that being said, we notice that they do have the exact same base. In this case, they both have 5. And anytime that you are dividing with those like bases, ultimately with the exponents, you're going to be subtracting them. So on the left side, we actually end up then with that same base, and we are subtracting our two exponents. Now, how you actually subtract the two exponents is, there's actually a couple ways that you can kind of consider things, but we're going to take the numerator first minus the denominator. All right, we even saw that in our previous, the definition of it. So we're going to take our numerator first minus the denominator. So minus our entire bottom. It's really important to note too that I'm throwing that bottom in parentheses. Okay, and the reason for that is because the negative that you're subtracting is actually going to be distributed to the x as well as the negative 3. All right, but on the right side we know that this is equal to 25. So now on the left, we still have our 5, that base 5, and we still have our 4x, and we are subtracting, again, that negative was distributed to both items, so we're actually subtracting x, as well as when you distribute that negative to the negative 3, you're really adding 3, equals 25. Cleaning this up a little bit more, we end up with 5 raised to the 3x plus 3 equals 25. And now we're kind of in a conundrum. We're kind of like, well, we're trying to solve for x. Unfortunately, this doesn't have any exponent. It actually does. The number 25 does have an exponent. It's always considered to be, if it's not written, they're always assumed to be it's 1. And the reason for that is you could have any number, let's say we'll just go with 25. 25 raised to the first power is still just 25. Even the number 7 raised to the first power is still just 7. So anytime that they're not actually written, it's assumed it's 1. And the reason why that comes in handy is because right now they do not have the same base, but we can try and manipulate this guy such then that they actually do have that same base, in this case 5 that we're looking for. One way that we can rewrite 25 is the same thing as saying 5 times 5, or 5 squared. So 5 squared, again, is the same thing as 25. We can rewrite this now such then that it has that base that we're looking for. So when we do that, we have 5 raised to the 3x plus 3 on the left side, he hasn't changed, equals, instead of 25, we're changing him to 5 squared, and even that's really raised to the first power. Right now it's not going to play too much of a role, but maybe this guy has an exponent at some point, and then you would have to work with using your power to a power property. So that's why I'm kind of showing this step right here. So we end up then with 5 raised to the 3x plus 3 equals 5 power to a power, multiplying those two. So we end up then with 2 times 1 is just 2. Now that they have those same bases, again, that's what we pretty much had to do to be able to continue on to solve for that exponent. We can go ahead now and set those exponents equal to one another again if it is a true equation. If this is actually a true statement between this left side and this right side, if the bases are matching, the exponents have to be matching. And so from right here, we're just pretty much just trying to solve for x now. So we end up with 3x plus 3 is equal to 2. And as a result, we end up then with just subtracting 3 from both sides. So we have 3x equals negative 1. And then dividing both sides by 3, we end up with x is equal to negative 1/3. And so that would be our solution for example 5b from our 5.1 set of notes.